Good evening. This is Mrs. Bowen with the University of West Florida, Elements of Statistics, and we are covering the t-distribution with confidence intervals tonight. We might go ahead and cover a little bit more. I'm not sure how much time we're going to have, so we'll just have to see how far we get in our lecture. Okay, so the t-distribution was developed by Mr. Gossett in 1908 and published under the pseudonym Student. As a result, the t-distribution is also called the student's t-distribution. The t-distribution is similar to the normal distribution, the z that we've been talking about, the z tables, okay, the normal distribution in some respects. Like the normal distribution curve, the t-distribution curve is symmetrical, okay, bell shape, about the mean, okay, so it's symmetrical with the mean in the center. It never meets the horizontal axis, so it has an asymptote. The total area under the t-distribution curve is 1.0 or 1%. Those are all the same as the normal distribution. However, the t-distribution curve has a lower height and a wider spread than the standard normal distribution. So our standard normal may look something like this, where the t-distribution looks something more like this. Okay, so it doesn't go as high and it goes out wider on each end. However, as the sample size increases, so as our sample size increases, the t-distribution approaches the standard normal distribution. The unit of the t-distribution are denoted by t. So instead of having a z like we do in the standard normal distribution, we're going to use the symbol t. Okay? Conditions under which the t-distribution is used to make a confidence interval about mu. Okay? First, the t-distribution is used to make a confidence interval about mu if, number one, the population from which the sample is drawn is normally distributed. That's extremely important, okay? We have to know that we're pulling our data sample from a normal distribution. Number two, the population standard deviation, sigma, is not known, okay? We were talking about in the last lecture about doing confidence intervals when we know what sigma is equal to. We use the t-distribution when we do not know what the population standard deviation is equal to. The t-distribution will have n minus 1 degrees of freedom. So df stands for degrees of freedom, and it is equal to n minus 1. So it's the sample size minus 1. So find the t for 16 degrees of freedom and a 95% confidence interval. So we went over this today a little bit, actually a lot, in our class time. If you've not been joining us during the online class time between 9:30 and 10:45, I strongly encourage you to start attending. It's been very, very beneficial to the students who are attending, and we're making sure that everybody's learning everything that's necessary to do very, very well in the course. So please join us. Okay, so as I said earlier today in our class online, this and this you will not be using during mod 7. This is mod 8, okay? And then this right here is what we're going to be using for mod 7. So mod 7, and that's going to be highlighted yellow so that you know that those go together, okay? So we have 3 rows. The first 2 rows, the top 2 rows, you're going to learn about in mod 8, okay? You're not going to learn about them tonight. For mod 7, for confidence intervals, this is what we're going to be using, this row right here, okay? So it says find the value of t for 16 degrees of freedom and 0.995 confidence coefficient. So we're going to put 0.95, we're going to put a comma, and we're going to put 16. That's how we write this, okay? We're going to write it as T sub C for confidence coefficient, comma, DF. and that stands for degrees of freedom. Remember that your DF, your degrees of freedom, is equal to your sample size n minus 1. Okay, so make sure you write that down. So it says, let's find it for T for 16 degrees of freedom and 95% confidence interval. So we're going to come, DF is this column right here. So all of these right in here are your DF, okay? So this is your DF. Highlight it in blue, okay? And then all of this in here, actually, I'm sorry, this over here is your confidence coefficient. So your confidence coefficient is right up here, and that is C. So all we're going to do is say our confidence coefficient is 0.95, so we're going to come over here to 0.95. And then our degrees of freedom is 16, which is right here. And we got this right here, and we're going to look at the intersection of the two, which is right here. So our T, 0.95, and 16 degrees of freedom is equal to 2.120, okay? So this is our new critical value, okay, or our T value, okay, like a T-score. It says find the T for 10 degrees of freedom and 99% confidence. So we're finding T for 0.99, comma, and 10 degrees of freedom. So we'll write 10 right there because it tells us how many degrees of freedom. And again, we're not going to be using this, and we're not going to be using this. I do recommend that you have your T-tables printed out for you. So we're going to come down to 10 degrees of freedom, and then 9.99, which is this row right here. So 10 all the way across is right there. So 10, again, right here. So our number is going to be 3.169. So this is equal to 3.169. Alrighty. Notice that I have 0.99. I did not have 0.999. So make sure you pay attention to which column you're grabbing your number from. And I would also recommend that maybe during your exam time or while you're doing homework even, that you have a blank piece of paper, just a blank piece of printer paper that you can just simply kind of hold down, and so you can go across. If you cover this row up here, okay, then this row here where you need to get your value from will be visible, and that will help you make sure that you get the value off of the correct row and you don't grab the wrong number and making a mistake. Okay, so confidence intervals for when mu when sigma is not known. Okay, so when sigma is not known, our confidence interval formula looks very much like our confidence interval formula for when we do know sigma, the standard deviation for the population. The only difference is instead of using a z-value, we're going to be using a t-value. And instead of using sigma, we're going to be using S. Those are the only differences. Everything else is the same. And again, to obtain the value of T, we're going to use n minus 1 degrees of freedom and then the given confidence interval or confidence coefficient. Dr. Moore wanted to estimate the mean cholesterol level for all adult males living in Hartford. He took a sample of 25 adult males from Hartford and found that the mean cholesterol level for this sample was 186 with a standard deviation of 12. Assume that the cholesterol levels for all adult males in Hartford are approximately normally distributed. Construct a 95% confidence interval for the population mean. Alrighty. Here's what's so important. When you read this through, you have got to be very careful about reading the grammar properly. You're going to look closely at the terminology that is used for the word problem to determine if this is going to be a T confidence interval or a Z, whether we're going to use a T or a Z. If we are given the population standard deviation, let me go back up here just a little bit. If we're given the population standard deviation, that means we have sigma, which means we're using a z, okay? You will look for words such as it is known, it is known that the standard deviation is. When you see the words, it is known that the standard deviation is, that's telling you that we know that we have sigma and therefore it is z. Okay? So we're going to also look then for something that says something like a sample standard deviation was taken. That tells us we have S and therefore we will be using T. You're going to look for the words like a random sample was taken and we calculated the mean, the mean and standard deviation. And that's going to tell you that we have S, which is a T, okay? So when you have to look at the sentence structure, and if it defines that we have a random sample and it says it was determined from that sample, or we gathered from that sample this mean, and then we go into standard deviation, that's telling you that the standard deviation is also calculated from that sample. Therefore, we have S, therefore we are using the T distribution. So pay attention to that grammar. It's going to take some practice. I'm just going to tell you up front, it's going to take some practice for you to get good at it. But the good part is we have lots of homework and you can practice. So, and I'll put some optional exercises out for you also to help you just simply read through and determine TZ, and that'll help you out also. Okay, so as we read this one, it says, he took a sample of 25 adult males from Hartford and found that the mean cholesterol level for the sample was 186 with a standard deviation of 12. So both the mean and the standard deviation came from this sample right up here, okay? So this is definitely X bar that we have. We found out that X bar is equal to 186. We found out that S is equal to 12 and N is equal to 25. Okay, and we're being asked to construct a 95% confidence interval, and I'll just abbreviate that as CI. Okay, and when I solved my problems when I was in college, this is exactly what I did. I read through the problems, I wrote all of this information down here, and then I would start solving. Okay, the first thing I need to do after this is recognize that I have a sample standard deviation. That's going to be a t-test, t sub 0.95, comma df. Our degrees of freedom are equal to n minus 1. Our n is 25. So it'll be 25 minus 1, which is 24. So we'll look 24 over here, okay? So we're going to come over and look at our tables, and we're going to look at 0.95 and 24. So here's our 0.95. So it's 1, 2, 3, 4 from the left, and we're going to come down here to 0.20 or 24 degrees of freedom. That's 24 degrees of freedom. I'm going to come all the way over here, and I'm going to go 1, 2, 3, 4. So this is my value right here, which is 2.064. 2.064. So again, we're going to come over at 24 degrees of freedom, and 2.064 is underneath 0.95. Okay, so that's how we found that. So right there, 2.064. So this is 2.064. And we're going to use the same formula that we've been using for confidence intervals, except we're just going to have a small minor change. So to calculate our confidence interval, it's going to be X bar. Again, this is our point estimate. And And we're going to add to that point estimate and subtract from that point estimate. When we subtract, that gives us our lower bound. When we add, that gives us our upper bound. What are we going to be adding and subtracting? We're going to be adding and subtracting our margin of error. And E is going to be equal to T, C, comma, DF for degrees of freedom, times our standard deviation divided by the square root of N. Okay, so I'm just going to write that over here. It's T, C, comma, DF times S divided by the square root of N. Okay, the other confidence intervals we've been doing, when we have known what the population standard deviation is, we would use a Z instead of a T, and then we would use our sigma instead of an S. So those are the two changes that we've made. So let's go ahead and calculate this. So this will look like 186, that's our point estimate, okay, plus and minus our T, which is 2.064, parentheses, S, which is 12, divided by the square root of N, which is 25. Okay, I'd encourage you on that last substitution, even if we have a perfect square as a sample size, such as 9, 16, 25, 36, go ahead and write it in properly, so in case there's a mistake somewhere when I'm grading your work, I can see that you substituted in the proper value and that you didn't reduce it. It's just a good habit to go ahead and get into of putting in the actual sample size there. So we're going to grab our calculator and we're going to find then that this is equal to, let me open up my calculator over here, and put it on over here, we'll turn it on, and we have 186 minus 2.064 times 12 divided by the square root of 25. This will give us our lower boundary. So our lower boundary is 181 point, let me pull that back up again, I didn't pay attention to the decimals. 0.064, we'll just go to 2 decimal places, and so that will be 0.05. So we're going to put a parentheses right here, a comma, and now we're going to calculate the upper bound. Like I taught you before, you can go up 2 clicks, that'll now be highlighted, hit enter. That repeats that equation, whatever you had in before, and now I can use this button here and go backwards until I get to that subtraction sign, and now I can turn it into addition and hit enter. Now I don't have to hit everything in a second time. And this is 90.95. So 90.95, so 190 rather, 0.95. Right here, this is my lower limit. My lower limit. This is my upper limit. Okay, and it's important that you always put your lower limit on the left, your upper limit on the right. Order is very important, okay? So we are 95% confident that the true population mean for the cholesterol level of men, adult men that live in Hartford, is between 181 to, I would say, 191 points. Okay, let's move on to our next example here. Okay, according to a survey, the National Collegiate Athletic Association Division 1 women's head basketball coaches conducted by the Women's Basketball Coach Association, the mean base salary, so the mean base salary of such coaches is $44,961. This was back in 1994. I'm sure it's significantly greater these days. Assume that that this survey is based on a random sample of 20 head coaches, so our sample size is 20. Further assume that the current base salary of all such coaches has an approximate normal distribution, and that the sample standard, that should be standard, sample standard deviation is 6,255. Determine a 99% confidence interval for the mean, population mean salary. Okay, so let's write down everything that we know. We know that the mean base salary, X bar, is 44,961. We know that our sample standard deviation, that does say standard deviation, you just can't quite see it. It's kind of invisible right now. So that's S is 6,255. We know that our sample size, N, is equal to 20, and we're looking for a 99% CI. Okay, and therefore I know right here that my DF is going to be equal to 19. Okay, and I know I'm going to be using my DF because I have sample standard deviation, not my population standard deviation. And I know that clearly on this one because it says sample. Alrighty, so the first thing I want to do is find my critical t-value. So it's going to be 0.99. So 0.99, comma, degrees of freedom, 19. We're going to pull up our t-tables. If you've got your t-tables, feel free to pause the video, find it, and then see if you get it right. If you're not quite sure, you just want to work with me, that's fine too. So we're coming into where C is equal to 0.99, which is this column right here. And then we have 19 degrees of freedom. So we're going to come down all the way down here and come straight across and look at the intersection. And we see that our value is 2.861. So that's 2.861. So now let's just write down the formula that we need. Again, it is X bar plus or minus our critical value, which is going to be 0.99, comma, 19 times standard deviation divided by the square root of N. And you know what? What we haven't done is we haven't looked at our formula sheet. Let's look at our formula sheet for a moment so you can see how this is written. Again, confidence intervals are on page 3. So we'll get over here to page 3. And so we have one sample, that's what we're dealing with right now. We're going to get to 2 samples, but that's not tonight. And confidence intervals for mu. And yes, you can do confidence intervals on your standard deviation, variance, and different other parameters, okay? But right now we're talking about the mean. And right now we're talking about when sigma is unknown, okay? When we don't know the population standard deviation. And so the confidence interval for that is going to be the lower limit is the point estimate minus the error. The upper limit is the point estimate plus the error. So our point estimate is, where does it say? Let's see here. Does it say it on here? I don't think it actually identifies the point estimate and makes that connection. You're just going to have to remember that since we're doing an interval, a confidence interval about mu, that we would need the point estimate for mu, which would obviously be X bar. And then our error is our critical value for t multiplied by our standard deviation divided by the square root of n. And we get our critical value for t based off of our degrees of freedom. Okay, so that's how it appears on your formula sheet. Alrighty, so coming back into here, let's substitute in everything that we know. Again, this is our point estimate. Okay, I have a lot of students in the past that have even to the final, not understood what a point estimate is. So that's why I'm writing it down, because I really want this class, I want 100% of my students to understand what the point estimate is. The point estimate is simply the best estimate based on a sample for the population parameter, okay? So what's our best estimate for the population parameter mu? It would be X bar. And then we're going to add and subtract from that the error, E, and E is equal to T sub C, in this case, it's going to be 0.99 and 19 degrees of freedom, multiplied by our sample standard deviation, divided by the square root of n. So X bar is 44,961. We're going to add to that, subtract from that T, which is 2.861, parentheses, multiplied by our standard deviation, which is 6,255, divided by the square root of n. N is 20, so that goes right there. and that is our formula. So now we're going to open up our calculator and figure out what that is. So open this up, turn it on, we'll clear it out so we don't get confused with our last bit of data. And we're going to put in 44,961. We're going to subtract off 2.861 multiplied by 6,255, and we're going to divide that by the square root of 20. Hit enter, and that is our lower bound. So our lower bound, since we're talking about money, we're only going to go to 2 decimal places. It's going to be $40,959.43. Okay, so $40,959.43. Let's see if my mind can memorize that one. $40,959. So 40,009. That would be a 9. 959.43. So this right here is our lower bound. Okay, now we need to calculate our upper bound. And our upper bound, let me make sure I got that down right. I did 40,959.43. Yep. Now again, the shortcut is simply going up twice with this arrow button right here, okay? Hitting enter. Now that brings that equation down. So now we're going to use this one to scroll to the left until we get to the subtraction sign. Once we get to the subtraction sign right there, see it's highlighted and blinking. We're going to change that to addition, and we're just going to hit enter. And now our upper bound is $48,962.57. We're going to round up accordingly, so it's going to be 57 cents. So 48,962. 48,962, 48,962, and oops, and 57 cents. And I just want to double check that. 48,962 and 57 cents. Sure enough. Okay, so this is our confidence interval about the mean for the average price or average salary for what was that? What type of coaches? Let's see here. National Collegiate Athletic Association Division I women's head basketball coaches. Okay, so in 1994 anyway. So this would be their was it 99? Yeah, 99% confidence interval right here. Okay, so we're 99% confident that the expected mean for the population would be contained within this interval. Okay, and this is the upper bound. Let me label that. Upper bound. And another way of saying this is that 99% of the time that I go out to the same population and collect a sample size of 20, 99% of the time that I calculate the average mean of those 20 randomly selected head coaches, the mean of those 20 coaches will fall between this lower boundary and this upper boundary. Okay, 99% of the time that I pull the salaries from that population. Alrighty, let's see what's next. We're switching topics. Let me do a quick time check. We're doing super on time. So now we're going to be talking about a different parameter. We've been talking about confidence intervals containing mu, the sample mean. Now we're going to be talking about confidence intervals about a parameter P for proportion. Okay. So the confidence interval for the population proportion, which is denoted right here by this P, is equal to P hat plus or minus Z times the sample standard deviation about the proportion. The value Z is used here to obtain the standard normal distribution table for the confidence level given, and then we have our standard deviation about the population proportion is this formula right here. So let me tell you some of the must knows. One of the things that you must know is one, if you are doing a confidence interval about, you will always use a Z. Always. You're never going to use a T. If it has to do with proportion, it is a Z. Period. Okay? If you're dealing with proportion, again, you will always be dealing with the standard normal distribution, Z, every time. Okay? Your standard error about the proportion is going to be the square root. Okay, so number 2, the standard error about the proportion denoted by p hat is going to be equal to p hat times q hat divided by n. P hat is our best estimate right here, our best estimate for our population parameter proportion. So this is right here, this is our point estimate, is p hat, okay? So p hat is our point estimate, okay? So this right here is our point estimate. We're always going to use a Z because it has to do with proportion. And then in order to calculate our standard error about proportion, we're actually going to use p hat and q hat divided by n. Q hat is equal to 1 minus p hat. So that also means that p hat plus q hat is equal to 1. Okay? So these two numbers together right here must add together to 1. If they don't, you've got an error. Okay? So again, the two numbers that you plug in right there must sum to 1. If they don't, you have an error. And then n is simply our sample size. So let's talk about population proportion and do an example on this. Let's see here if I can. So in a USA Today, CNN, Gallup telephone poll, there we go, 1,007 adults, 45% of them said that cigarette advertising should be banned. This was in 1994, okay? So the first question, let's just go ahead and write down some of the things that we know concerning this. And I'm going to go to a little bit thinner ink, and I hope that that's okay for everybody. But when it comes to population proportion and writing, there's a lot more numbers to write. And with the thicker ink, I kind of run out of room sometimes, and things blur. So I want to make sure I get everything written down right. So our sample size, N, is going to be equal to 1,007, okay? Because it said we did a poll, a telephone poll, and we spoke with 1,007 people, okay? And then it said 45% said that advertising should be banned. And this is what we're going to be talking about, is what cigarette advertising should be banned. So that's going to be P. P is going to represent the topic that we're studying, okay, or that we're interested in learning more information about. And so P hat in this case is equal to 0.45, okay, because 45% said that they were interested in having cigarette advertising be banned. So this is 0.45. Now, if P hat is equal to 0.45, Q hat is going to equal to what? Exactly, 0.55, because P hat plus Q hat must sum to 1, okay? They have to. So if we're given that P hat equals 0.45, that tells us that Q hat has to be 0.55. So that's what we know to begin with. And it says, what is the point estimate for the population proportion? That's our question. Remember, what they're saying is we need the best estimate for the population proportion. The best estimate for the population proportion is going to be P hat, which is equal to 0.45. You don't even have to do any calculations. You just have to know the definition. And then it says, what is the margin of error for this estimate with a 99% confidence level? So in order to calculate that, we need to know what is Z, okay? If we have a 99% confidence level, so we know that right here that our confidence level is 99%. That is our confidence level. Our confidence coefficient is going to be equal to 0.99. If our confidence coefficient is 0.99, our alpha is 0.01, because just like p hat and q hat have to sum to 1, our confidence coefficient plus alpha must sum to 1, okay? And then whenever we're talking about the confidence intervals, that tells us we have to split our alpha, what the error that we're willing to live with, our margin there that we're willing to live with, in each tail. So that tells us that alpha half is going to be equal to 0.01 divided by 2. So that is 0.005, okay? So I go over all of that because if I want to know what my z-value is at 0.005, that tells me that, again, for everybody who needs a little bit of a refresher, when we're looking at our confidence intervals, we have right here, and here we have our CC, or 0.99% of the area taking account. In each of these areas, we're putting half of alpha, okay? Half of alpha in each of those, and this is equal to 0.005. So again, this is equal to 0.005. So if I take this number and I add it to this number and I add it to this number, it better equal 1.0, okay? So to find the z-value that corresponds to this, I can go to my z-tables and I can look up 0.005 and I will get the negative value. So I can come in here, pull up my z right here. We're going to look under the curve for 0.005 and 0.059. It's going to be right here between the two of these. So it's negative 2.575 is the best number. We're learning right now that web work is requiring negative 2.58. So I'm going to, I hate not being precise. I really want to be precise. But for the sake of continuity and the fact that you will be doing this in web work, I'm going to go ahead and use negative 2.58, even though 2.575 is the best value for it. But because you're going to be doing this in homework, I want to use the right value for you that you have to use. So this is going to be negative 2.58, and whatever the negative is, it's going to be positive over here, 2.58. Okay, so that's our z-value. Let me go ahead and rewrite this over here. So z is going to be equal to 2.58. Again, a better option is 2.575. But if we also scroll down on your z-tables, right down here, it's going to have, for 99%, 2.58. I do want you to make sure that you know how to do this because you will be asked to solve this for values that are not listed here on your exam. So you need to make sure you understand how to interpret alpha, look up half alpha, and get your important values there for your critical values of the z. So now the next thing I want to do is let's go ahead and look at your formula sheet for confidence intervals about your proportion. Okay, so right here is the error. They have z sub c, so whether you put 0.99 or put your alpha value, you can tell whether we're talking about confidence level or the confidence coefficient or alpha based on the value. If it's going to be alpha, your value is going to be 0.25 or less. If you're talking about your confidence coefficient, it's going to be 0.75 or more. Okay, so that's how you can tell which one you're in reference. And then it's the square root of p hat times q hat. Instead of putting q hat, they put 1 minus p hat, which is the formula for what q hat is equal to, divided by n. Okay, and then where p hat is x divided by n. So n being your sample size and x being how many observations meet the requirements for what you're studying. Okay, and then again, it would be the same as down here, your point estimate, which would be p hat plus and minus your error, which would be this value plus and minus this value right here. Okay, so margin of error is what we're being asked for. So that is going to be E is going to be equal to 2.58 divided by the square root of P, which is 0.45, times 0.55 divided by N, which is 1007. And we're going to put this in our calculator, and we're going to find out that E is equal to 2.58 times the square root, making sure that all of this is underneath the radical, 0.45 times 0.55 divided by 1007. So our E is equal to 0.0404475828. Now, I haven't talked about this yet, but this is extremely important. Whenever you do proportions, when you're dealing with proportions for hypothesis testing or confidence intervals or anything, always, always, always go to 6 decimal places, okay? Very important that you go to 6 decimal places. The reason being is, one, the proportion is very sensitive to changes. So if you were to do calculations only to 2 decimal places, the final answers and results that you get will be so far off, it's not even comparable, okay, number one. Number two, if you take and you go to 6 decimal places and then we multiply this by 100, what do we really have? 4 decimal places of significance, okay? So by going to 6 decimal places in this form, if we go to our final form, multiplying the answer by 100, then we would only actually have 4 significant decimal places. And if you only went to 4 decimal places in this form, multiplying that answer then by 100, you would only actually have 2 decimal places. So again, when it comes to proportion, always use 6 decimal places. So this is going to be 0.040448. 040448. So 040448. So that's 1, 2, 3, 4, 5, 6 decimal places. Okay, very important. And then it says find the 99% confidence interval for the percentage of all adults that would favor banning cigarette advertising. So our 99% confidence interval, okay, is going to be our point estimate, which is 0.45. So it's going to be our P hat plus or minus our E, which is going to be equal to 0.45 plus or minus 0.040448. First number we're going to get is our lower bound. The second number we get is our upper bound. So we're going to come in here and we're going to go 0.45, subtract, doing our lower bound first, 0.040448. Put in our enter. So now that is so it's 40, 95, 52. So 40, 95, 52, like that. There we go. Now we're going to get our upper bound. We're going to go ahead and highlight this right up here, hit enter, and then I'm just going to scroll back over here very quickly and turn that into a plus and hit enter. And now that is 0.490448. So 49,448. So 49,4. So 49,448. There we go. So our 99% confidence interval for the percentage of all adults that would favor banning cigarette advertising is between 0.409552 and 0.490448. Essentially, 41% to 49% of the people would be in favor of banning cigarette advertising. Alrighty, next problem. An International Mass Retail Association surveys 1,006 U.S. households. 29% of the households said that Saturday is their favorite shopping day. That was in USA Today, 1993. Construct a 95% confidence interval for the proportion of all U.S. households for whom Saturday is their favorite shopping day. Okay, so let's go through and highlight what's important. So it says we did a survey of 1,006 people. 29% of the households said that Saturday is their favorite day. So if I'm doing a survey and I say, what is your favorite day to do shopping, and you say Saturday, that is what's considered a success. Okay, and so that would be marked yes. That would be a success. Okay, and then if you said another day than Saturday, then that would be in essence a failure. Okay, and so that would be how we would determine how many people actually said yes on Saturday being their favorite shopping day. Construct a 95% confidence interval for the proportion of all U.S. households for whom Saturday is their favorite shopping day. Okay, first thing I want you to notice, it says proportion. This right here tells me that I am doing a confidence interval about P, okay, because it says proportion, okay? I don't want you to be one of the few students that comes to final is trying to do sample mean on problems like this, okay? Pay attention to the wording and know what it means. So it says proportion, so I'm going to do a 95% confidence interval about P, okay? 95% confidence interval about P. And then it says that P hat is equal to 0.29. If P hat is equal to 0.29, that would mean that Q hat, that's a sad looking hat, let's make that a happier hat, there we go, Q hat is equal to 1 minus 0.29, and that is equal to 0.71. What's my sample size? My sample size is N is equal to 1,006, okay? So I've taken care of all the information that I highlighted, and I know exactly what I'm doing. I'm doing a confidence interval. If I'm doing a confidence interval about the proportion, I know for a fact that I am on the Z distribution. So I'm going to be looking for Z, okay, at alpha half. My alpha, if my confidence coefficient is equal to 0.99 or 95, that tells me my alpha is equal to 0.05. Half of alpha is 0.025. And I need to find alpha 0.025, and that is going to be equal to, looking under the curve in my tables here, I'm going to look for 0.025. So 0.025. Right here. Okay, so it's negative 1.96. So I have 0.025, that's half of alpha. I'm doing half of alpha because I'm doing a confidence interval, okay? I have to have half of alpha in the lower tail and half of alpha in the upper tail. And so therefore my confidence, or my Z critical value is negative 1.96, okay? So on my left one is negative 1.96. On my other side, it is positive 1.96. And if you put plus or minus right here, that actually goes right along with the confidence interval, okay? If you think about it, because we have our point estimate, P hat, plus or minus Z, okay, 0.025, plus or minus, okay? The square root of P hat, Q hat, divided by N, okay? And this is, I should have probably just put alpha half right there. In fact, I'll change that to alpha half since I went ahead and just wrote a generalized formula. So alpha half. So this is what our formula for our confidence interval looks like. Now, what is P hat? P hat is our point estimate. Let me go ahead and write that in. That right here, this is our point estimate. It is not always given to you in the problem like right here. Sometimes we have to calculate it, okay? And we'll get to a problem not too long from now where we're going to have to calculate it, and that's where this formula comes in, okay? But sometimes it's given to us like it was in this one in the last problem. And then we have our critical value multiplied by the standard error about the proportion. So let's go ahead and substitute all these different values in, and I want to go ahead and get a little bit thinner of an ink, and we're going to go right here. So this is going to be 0.29 plus or minus z alpha half 1.96 on the square root of p hat, which is 0.29, multiplied by q hat. Q hat is 0.71. Divided by n. N is 1006. And we're going to get our lower bound first, and then we'll get our upper bound. So let's grab a calculator and put this in. We're going to put in 0.29, subtract 1.96, multiplied by the square root of 0.29 times, not divided by, times 0.71, now divided by 1006. We're going to hit enter, and we're going to get 0.2619595. Now again, I said I want to go to 6 decimal places, so that's 1, 2, 3, 4, 5, 6. Notice that the 6th decimal place right there is a 9, and that right after that is a 5. That means that 5 rounds that 9 to a 10. And when that happens, that 9 turns to a 0, and this 5 right here goes to a 6. Okay? So for proper rounding, I'm going to get 0.261960. Okay? So 261960. So right here, it's going to be 0.261960. Now, we're going to calculate our upper bound. Remember, all you have to do, if you have this particular calculator, is go up, highlight it, click on enter. It retrieves that whole formula. Scroll to the left, hitting the arrow button until you get to the subtraction sign. Make it addition and hit enter. And then we get 0.318040. So it's going to be 0.318040. So that we have a 95% confidence interval about the proportion of, let's see here, of households that said Saturday is their favorite day to go shopping. So it's going to be between 0.261960 and 0.318040. So basically between 26 to 32% of the population say that Saturday is their favorite shopping day, and that we're 95% confident that that would contain the true population parameter. Okay, determine the given sample size that we would need to estimate mu for a certain confidence level. Okay, there are times when your boss is going to come to you and say, I need you to go out and take a sample, and I need you to be 95% confident that you've got the true population parameter in there for the mean. Okay, well, gee whiz, I know that I need to be 95% confident about my results, but how big does my sample have to be to ensure that I can be 95% confident? And he might also say, or she might also say to you, in addition to that, I want the air to be bound to a certain number, okay? And so now you've been given parameters by your boss, and you need to go out and determine what sample size you need to take in order to meet those requirements that have been specified to you. Sometimes what happens is that you're given these parameters and their restrictions and the expectations are too high. Either it's too costly to go out and get those samples, or it's just not practical. Okay, it's just not something that can be obtained. So then people have to take them, start making compromises on the requirements. Did they really want to be 99% confident? Maybe they could be 95% confident and still be satisfied with the results. Or maybe the air doesn't have to be so strictly bound. Okay, so that's what we're going to be looking at right now, is determining the sample size for the estimation of mu, so that you can be confident to the level that you've been told that you need to be. So it says, given the confidence level and the standard deviation of the population, the sample size that will produce a predetermined maximum error of confidence interval estimate of mu is determined by this formula right here. N is equal to z squared, sigma squared, divided by E squared. Let's look at that formula also on your formula sheet. So when we come in here, it's right here, minimum sample size, okay? And this one right here is about the mean. When you look at this one, you can see this is for proportion because we're dealing with p's. This one here doesn't have any p's in it, so this is about mu. Now notice that this is written a little differently, where the square is on the outside. But you know your rules for exponents, and you know that this would be z squared, sigma squared, and E squared, okay? So both formulas are the same, mathematically speaking. They are just written somewhat different. All right, so let's get back over here. And it says, suppose the U.S. Bureau of Census wants to estimate the mean family size for all U.S. families at a 99% confidence level. At a 99% confidence level, it is known that the standard deviation, so when you see it is known, that's an indicator that you are dealing with the population standard deviation. So when you see it is known that the standard deviation for sigma for all sizes of families in the U.S. is 0.6. How large of a sample should the Bureau select if it wants the estimate to be within 0.01 of the population mean? Okay, so here's our formula. Let's write down everything that we know. We know that we need to be percent confident. Okay. We know that our population standard deviation, sigma, is equal to 0.6. We know that we want the error estimate to be within 0.01. That is E. Okay? So that's 0.01. So right here, this is E. So it says, how large of a sample should the Bureau be if it wants the estimate to be within 0.01 of the population mean? That's going to be your clue that that is E. Well, in order to calculate N, our sample size, we need Z, okay? Z is going to be determined by our confidence here. Remember, we're looking at a confidence interval that we're going to calculate. Therefore, we know that our confidence coefficient, our C, is 0.99. We know, therefore, our alpha is equal to 0.01 because, again, these have to sum to 1. If I'm doing a confidence interval, I have to take my alpha and divide it in half equally between two tails. So this is going to be 0.01 divided by 2, and this is 0.005. Okay? So my N, well, let me go back and calculate our Z. Let's determine our Z. So our Z, okay, at alpha half, which is 0.005, is going to be equal to, that says that we have that much area under to the left of the tail there, so 0.005. So 0.005. Again, it's going to be negative 2.575. But we're going to go ahead and use 2.58 simply because that's what WebWork would want you to use. So we're going to put 2.58. And we're just going to put the positive down because it's going to be squared. So our formula is going to be 2.58 squared times our standard deviation squared divided by 0.01 squared. And you might find that it's easier to go ahead and use the UWF formula that's on your sheet there, because then that would be 2.58 times 0.6. So let me write that down a little differently. Times 0.6 divided by 0.01, and then we'll square the result. That might just be a little easier in the calculator, all said and done. So let's go ahead and, oops, not that. Hold on, don't worry, I got this. Here we go. So we're going to turn on our calculator. We're going to clear it out. 2.58 times 0.6 divided by 0.01 equals, okay, now we need to square that number. So we're going to take that number, our answer. So I hit this up here and this because that gives me my answer, whatever the last number I calculated, and I'm going to square it. And it says, in order for me to meet the requirements, that I'm going to be 99% confident that my estimate will be within 0.01 of the mean, okay, that I need to sample 23,963.04 people. So 23,000, oops, 23,000. Let me go back to that again. 963.04. Now, can we calculate even this little bit of a person? No. So to guarantee that we are certain that we meet this requirement and this requirement, we always round up. Always round up, unless you get a whole number. Round up, okay? And so in this case, therefore, N is going to be 23,964 people is what it's going to take for us to meet. Okay, so the last thing we need to do is be able to determine the sample size when we're estimating our population proportion, okay? So if we're given a confidence level in the value of P and Q, the sample size that will produce a predetermined maximum error, E, of the confidence interval estimate of our proportion is equal to N equals Z squared PQ divided by E squared. Okay, so very similar to what we just did for estimating the sample size for our mean. Now we're going to be estimating the sample size necessary to meet certain requirements of our proportion. So I'm going to scroll up. Here's our formula that we need to stay focused on. And let me go ahead and bring up the tables down here. Here's our sample size, minimum sample size to meet our maximum error requirements. And so you're going to have PQ, and then it's Z divided by E, quantity squared. Probably a little easier to calculate than what I wrote down. And then I'm going to discuss this in just a moment. Okay, so Lombard Electronic Companies has just installed a new machine that makes a part that is used in clocks. The company wants to estimate the proportion of these parts produced by this machine that are defective. So that's what we're studying. If it's defective, we're counting it. The company manager wants the estimate to be within 0.02 of the population proportion with a 95% confidence level. What is the most conservative estimate of sample size that will limit the maximum error to within 0.02 of the population proportion. So let's write down everything that we know and that we learned as we read through. So we want the estimate error to be within 0.02. That's E. E is equal to 0.02. And then we want to be 95% confident. So 95% confidence interval. Notice we're solving for n. That's our question. Because we're dealing with proportion, okay, whenever we deal with proportion, we're going to be dealing with z, okay? Now, our confidence coefficient is equal to 0.95, and I know that because we're looking for a 95% confidence interval. If my confidence coefficient is 0.95, that tells me my alpha is equal to 0.05, because my alpha plus my confidence coefficient must equal 1. Because I'm dealing with a confidence interval, half of alpha goes in the left tail, half of alpha goes in the right-hand tail. So that means I need to look up half of alpha to know my critical value. Okay, so I know what my z is going to be equaling. So I have my curve. I put mu in the very center, which is going to be 0 on the standard normal. I have 0.95, my confidence coefficient in here. I have half of alpha in here, 0.025. I have half of alpha in here at 0.025, and I need to know what is my z value that corresponds to this picture. Well, the easiest way using our current UWF tables is just to look up this right here, which is 0.025. Yes, it'll give us our negative z, but that's okay. I know how to deal with that. Okay, so we're just going to look up our z right here and come in here, and we're going to look up 0.025. So 0.025 is right here. 0.025, the area under the curve. This is the left-hand tail because this is what our table here shows. We come in here and we find 0.025 right here. So our value is negative 1.96. So it's negative 1.96. So we know that we want to be 95% confident of our results. So we're going to have a negative z, which is negative 1.96, and then positive 1.96. Standard deviations from the mean is what we're going to be looking for. So we know that z is equal to 1.96. Now remember, n is equal to, our formula up here, it's z squared, or just z, 1.96, divided by our e, 0.02, all of that squared, multiplied by p, multiplied by q. We haven't discussed what our p and our q are, right? We've got to mind our p's and q's. When we look through this whole problem right here, you're going to notice that nowhere did it give us even an estimate for what the proportion of defective parts is. We have no idea. It doesn't tell us. So when we have no idea and nothing to start with, the worst case scenario is we let p equal 0.5, therefore q is equal to 0.5. That is the worst case scenario. It gives us the largest sample size that will meet these requirements. Okay, so in here, because we have no prior knowledge, we're going to put 0.5, 0.5. We're going to grab our calculator. Turn it on, and then put it in. So this is going to be parentheses 1.96 divided by 0.02 close parentheses, square it. Okay, so that took care of this part. Now I have to multiply it by 0.5, so times 0.5, that's my P, times 0.5, that's my Q, hit enter. So 2004, we have to sample 2004 parts. In this case, 2004 parts in order to be assured that we are 95% confident that we will be within 0.02 of the population proportion. Okay, it's a lot of parts, so that's when it comes back to how cost effective is it to determine that we need to be 95% confident. Maybe if we were only 90% confident, it would make it more cost effective. On the other hand, maybe it's no big deal to grab 2,401 parts. That's all going to be determined by management. Alrighty, so again, if you don't have a P&Q provided in your problem, the worst case scenario is going to be that you allow P equal to 0.5. And that is exactly what your formula sheet right here says. Right here, it says without an estimate for P, use P is equal to 0.45, or 0.5 rather. So make sure that maybe you put a little note here that says no P provided, use 0.5 or something. Just make sure you know what that means, okay? Well, thank you so much for joining me. Our time on Thursday mornings, Tuesday, Thursday mornings has been very productive and terrific. If you're not attending, you're really missing out. If you've made it this far into the video, I would like you to send me the code word Star Wars, and then I know that you made it all the way through. That was our first code word for this particular video, and I'm looking forward to hearing Star Wars from all of my students. Feel free to just send me a text, and remember, it doesn't matter what time of day or night that you send me that text, because I always keep my sounds off. You will not bother me. Join us Thursday morning, and we'll practice a lot of these concepts, and you have a good night.